This is a video clip of Chapter 2, Model Parametrization of System Identification class. In this video clip, in this chapter, we will talk about model types, how we classify model into many categories. We talk about the general model structure we assume before the process of estimating the system. And we give some examples of two classes of the model. One is time series model that used a lot in many applications in engineering, in finance, in other things. And state space model, this is one of the main one of the main classes we see in engineering because it represents the most general class of linear time invariant systems. Okay, so in this clip, I think I think in this clip I will give an introduction on the model overview and the general model structure first. When we talk about the model, as we give you some examples in the last video clips, we can classify the models into different groups according to different criterions. For example, the model can be single input, single output, okay, or which means in short we call it SISO, or the model can be multiple input, multiple output. Okay, what does it mean? It means that Y and U that we are interested in the model, this is input, right? The SISO, the input and the output are both scalar. It's a scalar signal. If the model is MIMO, the inputs and the output are vectors and can be vectors of different dimensions. In the linear system theory, we usually learn the concept in the most general case, which means is MIMO, but the calculation of several things can be explained simply by the SISO example. Okay, you will see in this class that we kind of interchange the examples in those two cases. Sometimes it's easier to understand from SISO first, but most of the time it's not hard to go to the most general case, which is MIMO. Okay. If we talk about the linearity of the model, of course we can split it into linear and nonlinear models. Okay. Can someone recall the concept of linear system? Okay, because linear system is actually the same concept of linear transformation. We call it a linear system if we think of a system as a transformation that maps U to Y. A linear system would mean when you apply, for example, if you have U1, okay, and you observe the output Y1, the representation is Y1 equals GU1, okay. Another time you apply the signal U2 and then you observe the output Y2. So your Y2 is G times U2. If the system is linear, it means that when you apply a linear combination of these two inputs, if the system is linear, okay, if you apply a linear combination of two inputs, okay, where this alpha is any scalar number, the linearity of the system suggests that you observe at the output as the same linear combinations of the output. Okay, this is called superposition property. If that holds, your system is linear. Otherwise, it is called nonlinear. For nonlinear case, for example, y equals u dot plus, sorry, maybe y dot equals y dot plus y equals u square plus u, for example. Okay. In the third category, the models can be split as parametric and non-parametric model. Okay, as we explained in the previous clip that a parametric model is the one for which you can parameterize the parameter in the model. For example, the one that we encounter a lot, a transfer function, okay, as plus a1, as plus b1, as plus b2, okay. In this model, you can specify that, oh, this is a second order transfer function, okay, and I parameterize it in a way that everything in the class of second order model can be parameterized using this expression, okay. As you vary, as you change the values of these coefficients, you give different models in that class. For non-parametric model is a model for which that you don't need to represent it in terms of parameter, and that allows you to explain, to understand the characteristic of the system. The most common example is frequency response of the system, Bode plot, all right. The step response plot, okay, step response, because I mean this is a type of of description of the system that are, of course, they are different from system to system. Okay, for example, if you see a Bode plot of the red line, okay, compared to the blue line, you will see that, oh, this must be the frequency responses from two different systems. The red one seems to be second order because the gain is decreasing at two corner frequencies points. Why the first system, why the blue one seems to be the first order system. Okay, so we look at the model description, but that model description is non-parametric. Okay. A model can also be classified by this property. It is time invariant or time varying. We see a lot of in the linear control system class, we start with time invariant system, which means that the coefficients of the model doesn't depend on time. And actually the representation here, if we look at the response, all right, the time invariant system is a system that the response, if we start from t0 and you observe the response at time t, okay, the time invariant system means that your response doesn't depend on where you start, when you start, okay, but it depends on how much time elapsed from t0 to t. Okay, you will see it from the response as well. If you observe, if you look at the system response from when you initialize, when you observe at time tau, okay, you start from tau and you want to observe at time t, the state transition matrix here would depends on the time gap t minus tau, okay, and some other terms about the input. For time varying model, So it otherwise, the response of the system at time t would also depend on when you start. And the example are, for example, the class that the coefficients of your linear state space equation would be something like this. These coefficients, instead of a constant matrix, it is a function of time. Okay. The model, you can also regard it in two domains, time domain or frequency domain. Okay. For time domain, of course, you look at the time domain equation, like state space equation. This is one of discrete time, right? If you look at the frequency domains, it means that you look at the representation in Z domain or S domain, okay? Things like this. Some example. So you should be familiar with the transform we learned from in EE, Laplace transform, and the Z transform. Okay, those are frequency domain we encounter a lot in EE. I would like to skip this one and explain the last one. The model can be deterministic or stochastic. So by the name suggests, a stochastic model is a model that contains some random variable or random signal. In this course, okay, we're gonna use a stochastic model. This is, for example, again, if we look at this linear state space model, you see that typically X is called a state variable, U is called input. Okay, but what is that input? In control system, this is a control signal to govern the state variable to behave as we decide. In the system identification point of view, that for system identification, you actually design the input waveform, okay, so that it stimulates your system to produce Y in order to make the system identification process valid. I think I mentioned in the overview that not all the input signals are good for system identification. For example, if you put 0 all the time, okay, if you're, of course, if you put 0 all the time, you would observe 0 at the output. But does that make any benefit for system identification? You got 2 0 signals, you know, as data pair. How are you going to estimate G, right? That's not that obviously not a very suitable choice. But I also mentioned that, oh, what about impulse input? Okay, you put a non-zero U for a very tiny period of time. Of course, you will get impulse response at the output. But are those data pair has enough information for you to estimate G? Okay, this is going to be one of a very important topic we will present in the next chapter. This is how we select an input signal. But go back to the concept here. I would like to I would like to emphasize that in system identification, we are the one who want to choose U so that it stimulates, you know, it excites the system in all frequency modes, and so that the output Y contains enough information about G so that we can estimate G properly. So if we are the one who design U, which means that we know formula, we know how to synthesize U. U is deterministic, right? Because it can be determined. When we talk about stochastic model, it means that the model contains some other random entities. Most of the times we model it that the equation contain some random noise. Okay, so this is called process noise. Okay, so in this case, this is called stochastic model. Without this term, the traditional state space equation we learned from linear system class, the blue one, the blocks, the blue one, the yellow one, this is deterministic model. In this class, okay, when we know the, let me mention that. In this class, we will focus on linear system, parametric model, time invariant, both time and frequency model, okay, and stochastic. Okay, this is the focus in this class. The general model structure has the following form. Your output Y, okay, is a response from two types of input, U and noise E. Use the matrix G and H here. This is called a transfer function. We use this notation as it's a function of backward operator Q minus 1. Okay. And when we use the term colon, semicolon, and theta, that means this transfer function is parameterized by theta, which is model parameter. In this general model structure, we represent it as MIMO. So Y can be vector, U can be vector, E is a random variable. We assume for simplicity that it is IID. IID is independent, identically distributed. Okay, which means whatever distribution E comes from, at each time t, all of these, all of those time points of the error are drawn from the same distribution, same parameter, have the same moments, for example, the same mean, the same variance, and they are independent across time t. Okay. And also for simplicity, we consider the zero mean noise. Okay. So with this property that we describe, so I put the parentheses that E is white noise. If you haven't heard of the term here, please review the video lecture or just read it from any random process textbook. Okay. Q inverse here is a backward shift operator, which means if you have Q inverse YT, it makes one step backward, which is T minus 1. I'm going to use also sometimes an L operator, which is the same thing, and it has other name as lag operator. So you see both of Q inverse and L in these handouts, because I mean it's shorter to use L. Okay, and what about Q minus 2? It means that you backward into 2 steps before. Okay. Both HG, these are transfer functions. For example, if I put one example here. Okay, so you can think of G and H as a transfer function or a linear filter that applies on U, applies on E, and we're going to talk about we're going to talk about restrictions or conditions on G and H very soon. But you see here that in this representation, the coefficient 2, 3.5 in G, that's one example of parameter theta. Okay, 0.7 here is a parameter in H. Okay, in terms of general model structure, G and H can be any order as you wish, and this is something that the user must define before the step of system identification. And last, I would like to mention that when you represent the noise here, this is the second moment of noise. We call it covariance. But because the noise is white noise, this notation, it means this is a delta function, T and S. So delta function returns 1 if T equal S and returns 0 otherwise. Okay, so that means with this notation, it means that the noise at different two time points will have no correlation at all, but it will have the covariance as the matrix lambda. Again, please notice that we use the vector term. Okay, that's why you see the transpose here, because the noise is a vector having the same dimension as no, it doesn't have to be the same dimension as y. But I mean, in general, it's n-dimensional. Okay, and from the concept of random process, random signal, the covariance of a noise must be a positive definite matrix. We call it PDF. Again, please review what positive definite means. It means a matrix in positive sense. Okay. Okay, we're gonna come back to this slide, but if I would like to mention that briefly now, that not all the parameters in the model can be used. We have a feasible set of theta. Let me mention the last one that is simple. Theta as the entries in the noise covariance matrix must be ensured that the covariance is positive definite. The second one, okay, G evaluated at 0 must be 0. Okay, what does it mean? This is YGU plus HE. The matrix G represents how the effects from U to the response Y. Okay, so it determines the intrinsic characteristic of the plant. This is how Y responded to the deterministic U. So when we have this condition that G at 0 must be 0, it means that let me give a counterexample, an example of G that violates this condition. It is 1 plus this, right? Okay, sorry. So if I have YT equals to this is G, okay. If I have Y equals GU like this, it means that because this is the example for when you evaluate G at 0, what is it? When Q inverse is 0, it is 1, right? It is 1. It is 1. So it means that the response from YT at the present time, because it's multiplied with the 1 here, the response from YT at the present moment will have an effect on YT. Okay, that's the example the illustration of the system G when it violates this condition. But what if G obeys this equation, this condition? It means that you cannot have constant here, constant at the numerator of G. Okay. So in that case, you will see that G U, the way G applies on U, it will just use the effect from UT minus 1, right? Because Q inverse here operate on UT, it gives UT minus 1. And that means UT minus 1 will have an effect on YT. It's only UT minus 1, not the present UT. So these conditions that we apply on G basically means that the response of YT can be only from the past input. That represents the causal property of the system. I mean, as soon as you present the UT, I mean, your YT doesn't have response from the instant input, but it must be from the input in the history, one step before, two steps before. Okay, that's a condition that represents causal system. And the second condition, h of 0 equals I. Let me mention again here that our model structure is y equals gu plus he. Okay, now our h is a matrix that multiply e. Okay, this is a matter of normalization. Okay, if they are not equal to I, for example, if this is 2I, okay, you can just maybe 4I for easier representation. If it doesn't obey this condition, if it's 4I, basically you can just define E tilde in another way. You can just define E tilde as 2 of E. Okay, so these 4 can be kind of factor in a scaling factor too. And then you will get H tilde, E tilde. Okay, and now your H tilde becomes I. So you can normalize in this way as you want. If it's for example, if it's a matrix A, okay, if it's a matrix A, and of course this A must be can be factor. You can just define your E again as the square root of this A and times E, and then you represent it with the new transfer function, the new noise. Okay. Okay. For the first one, H inverse and H inverse G must be valid, which means your transfer function H must be invertible. And when you consider its inverse with these two expressions, they must be asymptotically stable. Everyone should be reminded that stable filter, stable transfer function, in the discrete time sense, it means that the poles of transfer functions must lie inside the unit circle. Okay, this is a concept that you should recall. For the first one, we will have the explanation to support this, why we require these two when we talk about the use of model for prediction. For the general, if we simplify the general model structure, y equals gu plus he, when we represent here is MIMO, and when we reduce to the general to SISO case, you can represent it as some polynomial times y. This is a scalar rational transfer function, which means this is a numerator polynomial and denominator polynomial. Okay, these can contain, okay, I will give an emphasis on the polynomial b. Okay, polynomial b is the one that that associated with the input u. If you can recall the condition that g at when you evaluate the Q inverse operator as 0, it must be 0 from the previous condition. So you see here that the polynomial b starts from Q inverse. Okay, so b0 is 0. That means only the past input will have an effect on y. And let's take a look at the polynomial c and d. Okay, you see that the coefficient here is 1, which means with these two expression, it suggests that your polynomial, your transfer function h is 1, normalized to 1. Okay, and of course, for scalar, your noise is going to be scalar. The variance becomes a scalar, a positive number, lambda squared. Okay. For the special case, okay, when h term is I or 1 in this case, I mean for scalar, this is called output error structure, because if you subtract the measure output y from the model output, this is GU, okay, that gives you the error at the present time instantly. Okay, and this is output error structure. Okay, if we take a look at here, if this polynomial a happens to be happen to be 1, okay, so this is again a general model structure in this format, okay, where f and g doesn't have to be the same polynomial. Okay, I mean g and h, this represent g and h. D doesn't have to have no. These two guys don't have to have common denominator f and g. Okay. Let me briefly mention why we need a model after all the process of system identification. How are we going to use the model? That can be three purposes. One is for simulation, second one is for prediction, and the third one is for inference. Okay. For the simulation purpose, we use a system. We use the model to imitate the characteristic from the real physical system. Okay. So when we have y equals gu from he, suppose that we already estimate g and h. Okay, this is the estimate g, this is estimate h. Of course, in real life, you only have the waveform of u. Okay. For example, if I want to see step response, I would put u as a step input. Okay, but I know that in my real physical system, it also has the response due to noise. How are we gonna see the effect noise in the actual response. So you can generate E, okay, as random noise with appropriate variance. Of course, after the system identification process, the variance is something you have to estimate as well. So let me put it here. That's sigma square hat. Okay. In this picture, I simulate the dashed lines are noise realizations. The dashed line. You see that as you generate it randomly, the pattern of the noise have different sample part, different realizations all the time. The bold line is a response from GU. And in this example, I use the binary sequence of the input. Okay. So for simulation purpose, it gives you a sense of, oh, this is how the response Y I would see at the actual output when I have apply U this way and when and with the presence of noise. Okay. The second purpose of using the model is for prediction. Okay, this is the one for which you have the model and you want to predict the response Y in the future using the currently available information. We use the notation hat because it's a prediction, it's an estimate. We use the notation Y hat at time t. That means that you want to predict the response of yt. You want to estimate the value of yt given the information up to time t minus 1. Okay, let's take a look at the expression. There's going to be analysis behind this formula that we will explain in the subsequent chapters. But let me just give you the immediate result that if you have the general model structure, again, G and H are the transfer function that you eventually estimate. Okay, and this is the situation for which that after you obtain the estimate, this is how are you gonna synthesize the one-step prediction of Y. That means that you're gonna calculate the transfer function H inverse G and 1 minus H inverse. I used 1 here, but generally it should be identity operator, identity matrix. So when I calculate or compute the one-step prediction in this way, you will see that with the expression H inverse G apply on U. But because of this condition that we just 0 is 0. Okay, which means this transfer function H inverse 0 G0 is what? Remember that we have these two conditions previously. H of 0 is I, G of 0 is 0. By this notation, we implicitly means that H inverse exists. So this is I, this is 0. So the result is 0. Okay. That means in order to obtain Y at time t, you cannot use the information from ut, right? Because that means that you have you cannot have the constant term in this transfer function. In order to predict the step at time t, the only information you can use is ut minus 1, ut minus 2, and so on. Okay, this term as well, okay, because of the condition that H0 theta equals to I, so I minus H inverse 0 is 0. The result, the effect from yt cannot be present in order to predict y hat at t. Because, because if you knew yt at the moment, why would you need to predict y hat? Right? So the whole concept of prediction is you can only use the information up to time t minus 1. So this is just to kind of verify that this statement makes sense in terms of that this is an expression for one-step prediction. And again, let me emphasize that how do we get this formula? This is something we talk in the prediction error method around chapter 10. But let me express here. So once you predict y hat time t given t minus 1, so you can compare the quality of this prediction with yt, you know, in offline process. And this is a graph you get. The line is kind of it's a very thin line. Not sure if you can see the blue. The brown one is the actual output. And let me emphasize that the blue one and the red one, how are these different? So the blue one are the prediction from the estimated system, estimated model. The red one, I actually do this. Okay, so suppose my g hat is 1 plus 2.2345 Q inverse. Okay. Suppose the blue one is given by this. Actually, the red one adjusted system, I just manually kind of threshold the I mess up the color. I hope you're not confused. Okay, this is the adjusted one. I adjust it manually that, okay, let's, this is 4 decimal digit. If I just threshold, just approximate it 2.2, like this. Okay, this is the adjusted system. The key point, one illustration is to say that when you work with polynomial, rational, when you work with a rational transfer function, if you adjust the coefficients slightly, okay, it can change the locations of system poles dramatically. Everyone knows that the characteristic of the system depends on the poles and zero, right? Which are the roots of denominator and the roots of numerator as a zero. Then you will see that the result of fitting kind of changed from 70% to 66% just by naively threshold the coefficients. So this is something that you shouldn't do, actually. Okay. Let me also mention that this is just for illustration purpose. When you work in a real time, when you do the prediction is the following. The blue line is this is t, okay? The blue line is yt at the moment. When you do the prediction, it means that this is the time of performing the prediction. What you're gonna get is the response of yt. This is the estimate, right? If I change the notation a little bit, yt plus 1 given t. Actually, you're gonna get the red line as a prediction. Okay. Actually, when at the moment of you perform the prediction, you don't have yt plus 1 to be compared with. But this is the graph where, in this slide, this is a graph where you perform the prediction over a horizon, and then you collect everything as offline process to assess the performance of the prediction. I would suggest that you know, for the first and the second purpose, simulation and prediction, the computer code for these two tasks are readily obtained in many system identification package and very simple in system identification toolbox in MATLAB. Okay. For the last purpose of using the model, I would say that it varies from application to application. It varies from actually from the point of view where someone develop a model. These three bullets are examples that I think is easy to explain, and actually from my own experience of research. Okay, generally, when you develop a model, it means that you have some research questions in mind. If those questions are about examine statistical property of variable in your system, it can be something like in the following. Okay, if someone develop an autoregressive model, okay, we will talk about this model eventually. What does it mean by AR? But let's just say that, okay, it's a equation given by this. Okay, and then what more interesting is that your y is actually a vector. So A1 is a vector multiplied with the vector of the step t minus 1 plus A2, the vector of the step t minus 2, and so on. Okay, so in this case, after the estimation, which means that your aim is to estimate these AR coefficients, if it happens that there occurs 0 at the same locations of all the coefficients, let us say that this 0 location is the element 1, 3, 1, 3. It means that your YT element 1, okay, is 0 times YT minus 1 element 3 plus 0 times YT minus 2 element 3. In this case, it illustrates that the variable, the component 3, has 0 effect on the variable 1. Okay, this is the concept of a Granger causality in time series analysis. So it means that actually you're not going to use the AR model for prediction, for simulation, but you just want the model parameter to infer something. And in this case, to infer about cause and effect from one variable to another variable in the vector time series. In the second example, okay, this is from statistic point of view as well. When you have a random process and if you have a spectral density matrix S, okay. In this example, it's a spectrum from AR process, which means that the spectrum can be represented with some model parameters of AR process. Or, I mean, at the moment you can just say, okay, my spectrum has 3 terms. Okay, the one term is the matrix polynomial. Okay, matrix polynomial in frequency domain, and the polynomial is parameterized by these coefficients. You can just grab it in this way at the moment, because you may need to learn first about what the AR process. Okay, but given you know that the spectrum has this form, okay, and given one information that the spectrum, usually for vector time series or vector process, spectrum is going to be a matrix of n by n. Okay, is a matrix of a function of omega, frequency variable. So in statistics, if you take the inverse of spectrum, look at the ij element. If it happens to be 0, it signifies the conditional independence property. Let me mention that it actually under the Gaussian assumption as well, which means I need to also assume that if your stochastic process has Gaussian distribution, the 0 in the ij element of the inverse spectrum signify the conditional independence property, which means the corresponding component of your time series process, the component I, is independent of the component J, all right, conditioning on other variables. So you see here that if your S is parameterized by AK, so conceptually your S inverse is parameterized by A1 and AP as well. So after you estimate the process, which means you estimate A1 hat, A2 hat, AP hat, okay, the 0 pattern in the S inverse will give you the conditional independent structure of vector process, vector random process. Again, this is an example of model inference. I don't use the estimated process to look at distribution, to look at the to look at one sample part, to look at one realization. But what I am interested is to look at model parameter that help me explain this statistical property. And the last one may be easiest to understand. Okay, an example that, okay, for MIMO transfer function. Okay, everyone know that the transfer function is the relationship between that explain the relationship from U to Y. Okay, so H is generally a rectangular matrix. Okay, the dimension is dimension of Y times dimension of U. Of course, certainly if the entries in the transfer function is 0, here in this example, this is 2 by 3. If it's 0 here, it means that U, this is 1, 2, 3, right? This is 1, 2. The U3, okay, has no effect on Y1. Okay, if you look at this 0, of course, U3 has no effect on Y2. And if you look at this 0 at the element 2, 1, U1 has no effect on Y2. Again, this is an example that after you estimate the transfer function model, your focus is more about, okay, what is the relationship between input and output? I just want to characterize this aspect. So you can look at the 0 pattern in the transfer function. There can be more. I would say the term model inference is a very broad term. It depends on specific questions in mind you have when you develop the model. Okay. So this clip is all about the introduction of the general model structure. In the following clip, I will give some example of two model classes, state space and time series model.